Okay, welcome everyone to the last lecture, lecture 4 of Statistical Methods in Cosmology. Today you will really have to bear with me because I felt completely sick. Also, don't get close to me. So I'll do my best. All right, so, okay. So, sorry? Okay, so I just thought I would continue showing you. Yesterday we started talking about feature analysis, and today I wanted to show you basically how to use this formalism to plot error ellipses, okay? When, for example, marginalizing over, the rest of the parameters. If you just want to plot the error ellipse for 2 parameters, you marginalize over the rest of the parameters, and I wanted to show you how to do this. As a side note, I also have prepared for yesterday, but we didn't get the chance to look at it. But today I wanted to show you how to construct a minimum variance unbiased estimator, which is super useful in general in cosmology to know how to construct these objects for whatever, whatever you may need to estimate in your work. And after that, I will switch to slides, and I will be talking about wavelet scattering transform, which is something that I have been working on over the past few years with my group, and it's a technique that I'm very excited about, okay? It's a pity that today I'm a little bit toned down, so maybe you will not notice the excitement that I have for, for this topic. Okay, so yeah, so I wanted to talk, okay, so this is feature analysis continuation. And the question that I wanted to go over is how do you plot error ellipses, okay? So how do you plot error ellipses? Okay, so the idea is, oh, thank you. The idea is you have learned last class how you construct a Fisher matrix, okay? Say the Fisher matrix, say your problem has n number of parameters, okay? So you will have an n cross n Fisher matrix, yeah? Now, if you want to plot the error ellipse for 2 parameters, for example, you first want to project down to that space of 2 parameters, okay? Okay, so what you do is you calculate, this is the way to do it. First you calculate, let me put steps. You calculate the n cross n Fisher matrix, okay? Then you invert it, and in this process of inversion, you are making all of the parameters talk to each other, okay? So this is helpful for marginalization, okay? Then, if you're interested in a subset of 2 parameters, for example, okay, or 3 parameters, whatever you're interested in, you just take the subset that you're interested in. Say you're interested in 2 parameters, so you just take the 2 cross 2 subset of f minus 1, okay? Let's call that g minus 1, g to the minus 1, okay? This is the inverse of g. I will call that like this, okay? So basically, when you invert the inverse of g, you get g, okay? Get g, yeah, which is the subset of the Fisher matrix, but already marginalized over the rest of the parameters. And once you have g, we are talking, okay? You have the object of interest, yeah? So how do you deal with, well, Now you have the object of interest, which is the subset of the Fisher matrix over the two parameters that you want to consider, having marginalized over the rest of the parameters. And basically to plot the error ellipse, well, you just do, have G11 times G11 times plus 2 G12 plus G22, okay? And this will give you the delta chi squared, okay, for 2 degrees of freedom. 2 degrees of freedom, yeah? Now the delta chi squared for 2 degrees of freedom, let's call this 1 over F, okay? So to plot, for example, this is times the parameter 1. This is, I forgot that. This is times the parameter 1 and the parameter 2, okay? And this is times the parameter 2, sorry, and this is a square, okay? So alpha 1 and alpha 2 are the names of 2 parameters that you're, the 2 parameters of interest, okay? Great. So this is the equation for the ellipse that you want to plot, okay? Like, imagine you may have seen these plots, yeah, these error ellipses of the errors in both parameters, the 2D probability distribution function of these 2 parameters once you have marginalized over the rest of the parameters. So if you want to plot the 1 sigma contour, this F will take a value of 0.434, okay? This is for the 68.3% confidence level, okay? And say you want to plot the 2 sigma contour, this F, I call this delta chi square 1 over F. This F will take the value of 0.167 for 95% confidence level, okay? Okay, so this is the way you can basically have the error ellipses for all of the parameters in your model when you want to forecast errors for a future experiment. Or perhaps it's not necessarily a future experiment. Perhaps it's an experiment that is already existing, but you want to do a fast back of the envelope calculation. So this is what you can do. Any questions about this? Yes, Susana. Great. So this corresponds to 68.3% confidence level for a delta chi-square, for a chi-square distribution with 2 degrees of freedom. So if you have a chi-square distribution for 2 degrees of freedom, you integrate until you have 68% of the area. That's the number that you get. Other question? Okay. So this is what remained on feature analysis. Now, as a parenthesis, I wanted to talk about, I thought I would take the chance, since I had 4 lectures, to talk about how to construct a minimum variance and bias estimator. Okay. So this is the way to do it. In fact, I should start, yeah, I never included this in lectures on statistical methods in cosmology, but I think it's a good idea because, you know, we use this over and over in cosmology. You are constantly trying to build minimum variance and bias estimators of different observables, yeah, in the universe, and this may become handy. Okay, so minimum variance unbiased estimators. What do I mean by this before I go on into how to calculate these objects? You may want to, in cosmology, for example, we saw an estimator. When we first started, I told you that you could estimate the correlation function. Remember that we wrote the correlation function with a hat. I told you that you could estimate from the data the power spectrum. We're constantly building estimators of the quantity that we want to measure, okay? Estimators because we have one observable universe and you want to estimate the true correlation function or the true power spectrum. Or you may want to estimate, for example, from measurements of CMB lensing, you may want to estimate the gravitational potential. Yeah, there's a famous estimator for the gravitational potential that has been built by Wayne Hu and Okamoto a long time ago. You may want to estimate the optical depth to reionization. There are different quantities that you may think about estimating from the data, you see, going to the data and measuring this quantity of interest. So how do you do this? Imagine you have a set of already unbiased estimators, okay? So you already have a set of unbiased estimators DI. And by unbiased, I mean that when you take the average of these estimators, sorry, I should put a hat. When you take the average of these estimators DI, you get actually the quantity of interest. Okay? Okay, so the question is, how do you find, and this is very common, you may have, I don't know, a set of estimators for the CLs and you want to combine them into something else to find a minimum variance and bias estimator. So the question is to find the minimum variance and bias estimator linear combination of estimators, okay? So how do we do this? Well, so first of all, well, for simplicity, I will just subtract the mean of this guy, okay? So that I can write down the covariance, okay, of DI, DJ. This guy will be Cij, and here I'm taking the mean of DI equal to 0, okay? I'll subtract the mean of these estimators. Now, what you want to do is to find the best possible estimator, linear combination of these estimators. What's the best possible? In cosmology, the best possible linear combination of these estimators means the estimator that has the least amount of noise. That's minimum variance. I want to reduce the noise of my final estimator. So you may think, okay, well, I have some estimator that I call D, which will be a linear combination of these estimators DI, okay, with some weight. Yeah? Okay. So if I want to impose that this estimator D is unbiased, yeah, the condition of this estimator D being unbiased tells us that the sum over the weight has to be equal to 1, yeah? So that the expectation value of this estimator D is equal to this to its value, okay? So the condition for this guy being unbiased means that the sum over the weights has to be equal to 1. Okay? Okay, so we can enforce this constraint with a Lagrange multiplier. Yeah? Great. So we can say that, okay, so we can say that the variance, we want to minimize the variance of this guy, but with the condition that it's unbiased, okay? So let's write down the variance of this guy. The variance of this guy will be the sum over I and the sum over J of Wi, Wj, Cij, okay, plus some Lagrange multiplier times the sum over the weights minus 1. Okay, here I'm enforcing the condition of this full estimator being unbiased. Okay, I wrote down the variance of this guy, but now I want to take I want to minimize it, right? So in order to minimize it, I take the derivative with respect to the weights, and I make it equal to 0, okay? So when I extremize this guy to make it minimum variance, what I get is the following. I get 2 times the sum over J of, let's call it CKJ omega J plus lambda, when I take the derivative of this, is equal to 0. So this is equal to minus lambda. Okay? Okay, great. So now let me work in matrix notation, which will make our lives slightly simpler. Okay? So what I want to do is, well, I will write 2C, where C is this matrix, okay? W will be equal to minus lambda times E, okay? Where E is a vector whose elements are all equal to 1, okay? Is the identity vector. Okay, great. So the solution to this equation tells us that W, that's what I want, right? I know that the sum over the weights is equal to 1, but I want to know what are the weights to make this estimator minimum variance, okay? So what is the weight? Well, I know that W will be proportional to C to the minus 1 times this identity vector, okay? Or if you want, in index notation, going back to index notation, I will have that Wi will be proportional to the sum over J of C to the minus 1 Ij. Okay? Okay, and so the restriction that the estimator is unbiased, which is this, the sum over the weights is equal to 1, normalizes the weights, okay? And so I can write down, so I know that this is true, and I also know that the sum over all the weights is equal to 1. Then it's easy, right? I can just basically normalize these weights, and I can write down that the weights are equal to the following, are equal to the sum over J, C to the minus 1, which is the covariance Ij. And now I want to normalize this. So I sum over J and over K, okay? So the sum over j and the sum over k of c to the minus 1 kj. End of the story. I showed you the weights for a minimum variance unbiased estimator. You see? We have an estimator that is unbiased, whatever, unbiased means that when you, just like in the correlation function case, when you take the ensemble average of the correlation function, you want it to be the correlation function that you know is true for an ensemble of different universes, okay? Same thing, when you take the ensemble average over some estimator D, you want it to be D, okay? That means that it's unbiased. Minimum variance, it means that you construct some object that has the minimum possible noise, okay? And this may be useful. People have used these estimators, again, to construct, to estimate the gravitational potential from CMB maps or the optical depth to reionization, yeah, from CMB measurements. Yes. Say that again. Yes, yes. What I meant by that is so this is a work that I did many years ago, and it's not the optical depth. In fact, it's the inhomogeneous part of the optical depth. So yes, thank you. Yeah. Yes, I didn't build an estimator for the optical depth per se, but for tau of n, where that's the inhomogeneous part. Yes, good point. Any questions about this? No questions? Yes. For what, sorry? No, unbiased just means that the mean is equal to the object itself that I'm wanting to consider. Yes, the hypothesis, I mean, this is not for unbiased, it's in general the hypothesis of ergodicity, right? That the mean, but that doesn't necessarily imply that, yeah, the connection is not one-to-one. So unbiased means that the mean, that the average is equal to the quantity you want to consider. That it's not biased, that when I go and construct an estimator for phi, I will not get 2 phi. I will get phi. Yeah? Yes. Yes. That don't have any bias. I can construct estimators that are unbiased. Yes. Right. So you use so you observe, you measure quantity, right? You measure the CLs, and you want to know if the thing is that I can calculate the CLs for the ensemble average, but when I measure the CLs from a map, I want to know that that measurement is equal to the quantity that I measure, that I estimate for the ensemble average. So yes, I could construct an estimator for the measurement that is not biased. I mean, yeah. Yes. So I started with unbiased estimators here, and I wanted to make a linear combination of unbiased estimators to get an unbiased, to get a total unbiased estimator. Yes. then you have to make them unbiased first. Yeah. Other questions? Okay. This was an aside that I thought may be useful for you in the future or right now. And what I wanted to do now is to start talking about a technique that I have been very excited about with my group. For this, I will do the following. 1 second. Compartir, mostrar escritorio. Excellent. Okay, let me see this. You're not seeing what I'm seeing, so that's good. Great. So this is the last part. We arrived to point 10 of the different topics that I wanted to talk in this lecture, okay? And so I just thought that in the remaining time, I would talk about how, well, you know that we are expecting a deluge of data coming from cosmological surveys. We are taking data right now, you know, of different types of observables, the cosmic microwave background, the large-scale structure of the universe, galaxy surveys, gravitational lensing, Lyman alpha forest, you name it. Many different surveys are taking data right now, are being planned for the next decade. So we really expect a deluge of data coming from different cosmological surveys. And so a good question to ask right now is how to extract more information from them. Remember that at the very beginning of this set of lectures, I started talking about the correlation function and the power spectrum. This was under the, you can always take the correlation function or the power spectrum. But under the assumption that the field, whatever field you're estimating is Gaussian, all of the information will be contained in the power spectrum. Now, if the field has a non-Gaussian distribution, then you may want to extract, there will be more information besides the power spectrum. And in general, people, you know, over, you know, the traditional method has been to go over to calculate the different cumulants of the field that you're considering. Now, we have been thinking over the years about a method to extract non-Gaussian information that has certain advantages, and I wanted to talk about this. Before that, let me tell you a bit more about this deluge of data that I'm telling you that we expect to have in the near future. Basically, here I'm showing a compilation of Schlegel and Kohlmeier that where we can see that the number of redshifts measured by various surveys. I don't know if you see well. So this is the number of redshift, and this is the year, okay? And you can see that the number of redshifts measured by various surveys roughly increases by a factor of 10 every decade, okay? This is huge. We are around here where we have DESI in the future. You know, these are some of the surveys. And so we will have MegaMapper, but we will have a lot more. And so we are at the time in which a large collection of cosmological surveys are about to map very precisely the distribution of galaxies in the universe. And this will bring with it a lot of new information. So as I was telling you, it is a good time to ask, how can we extract as much information as we can from these different data sets, okay? Going beyond what has been done for many, many years, which is just to calculate the power spectrum of whatever field of interest you have. Yeah, this resolution, okay. I know you see it better there, I think. So in addition, I just thought this is a course on statistical methods. So I just wanted, there are some posters here on metrics for measuring tensions between different parameters. So I thought, you probably saw this in some other lecture, current cosmological tensions in parameters, but it's very relevant. There are tensions in cosmological parameters, and different statistical techniques to measure these different tensions are relevant. In the last few years, several tensions in the values of cosmological parameters as measured from different data sets have emerged. Well, I should say in the last many years, but in the last few years, they have emerged with more significance. So there is a tension of about, have you talked about cosmological tensions in some of the other lectures? Yes? Okay. In the discussion session, yes, I was there. So there is a tension of about 5 sigma now in the Hubble parameter value. And this is, anyway, the expansion rate of the universe today from probes, as you know, from the local universe and measurements from the CMB. And you can see this tension. This plot is really doesn't show up very well. Oof, I don't see anything. Is it me? Yeah, I don't see anything. Okay. Anyway, there is a tension. Late and early. You can see this is the early universe. This is the late universe. You can see that the error bars don't overlap. Yeah, you cannot see anything in this plot. So don't look at the plots, just listen to me. So there is also a tension in the value of the amplitude of the matter fluctuations today from measurements of the CMB and probes of lower redshift. By this, I mean the sigma 8 tension, okay, which is the amplitude of the power spectrum at 8 H inverse megaparsecs. And these tensions could be due to systematics, could be due to systematics in the CMB or systematics in the other surveys that you're considering. But if not due to systematics, could be due to new physics. And this would change dramatically, of course, our understanding of the universe. If there is new physics, we want to understand what is this new physics that is that would modify our standard model of cosmology. In fact, almost every day there is a huge, still now in the archive, you may see new models for dark matter, new models of dark energy arising to try to solve these tensions. Up to the day of today, I have not seen a good model that solves any of these tensions, but they exist. So this is just to say, not to claim that there are no models that solve these tensions, but to say from the, from the observational point of view, that it is important to measure these parameters with independent observables that have independent systematics, and also to do it as accurately and precisely as we can, okay? So, and by this I mean we may want to extract all of the information that we have from cosmological surveys. And if the field is non-Gaussian, there is more information coming that is not contained in the power spectrum. Okay, so this is all of this introduction is to start talking about this technique known as the wavelet scattering transform that I will explain right now. Okay, so let me introduce it by saying that, or motivate it by saying that, so the traditional way of analyzing cosmological data for about 20 to 30 years right now has been to compute the power spectrum of the different fields that we measure. But if the field is non-Gaussian, the power spectrum doesn't contain all of the information. And this is the case, for example, for the large-scale structure of the universe due to the influence of gravity over time, which makes the distribution of structures non-Gaussian, okay? Even if we start with a model of inflation in which the initial conditions are Gaussian, we know that we will end with a non-Gaussian distribution of structures in the universe. And this is because of gravity, okay? So we know that the distribution of galaxies that we see today are very non-Gaussian, is very non-Gaussian. Okay, so the usual, so you may say, okay, we know that the large scale structure of the universe is non-Gaussian, okay? Regardless of inflation, it will be non-Gaussian. Now, okay, so now you may say, okay, we need to go beyond the power spectrum because there is more information beyond the power spectrum. And the usual way to go beyond the power spectrum in cosmology has been by computing higher order statistics, okay, or these cumulants that I was talking about before, the bispectrum, the trispectrum, etc. Now, and so these are the higher order statistics when you go beyond the 2-point function, okay? One disadvantage of the higher point functions is that they fail at capturing all of the information when the field is highly non-Gaussian. And this is shown in a very nice paper by Caron about a little bit more than 10 years ago. So if the field is highly non-Gaussian, you cannot measure all of the information, even if to go up to higher and higher order point functions. And another well-known disadvantage is that it rapidly becomes computationally infeasible once you start going to higher and higher point functions, order statistics, okay? Because, okay, for the bispectrum, for example, you have to measure the triangles in the sky, yeah? But to measure the error bars, you need to run simulations, and measuring these triangles is more expensive than measuring 2-point functions. And when you go to higher and higher point functions, it becomes more and more expensive, okay, to run these simulations and measure the higher order point functions in order to estimate the error of the statistics that you're considering. It becomes really difficult. There is a reason why there are a lot more works on the power spectrum than on the bispectrum or the trispectrum on real data, okay? It becomes computationally infeasible. On the other hand, in recent years, there has been an increased use of machine learning techniques. For example, convolutional neural networks. That's a typical machine learning technique to extract information at the field level. And by this, I mean, in general, we measure a field and we take statistics of this field, the power spectrum, the correlation function, the bispectrum, to extract information. But what if you want to extract information from the field itself? Convolutional neural networks, for example, have been used over the past few years to extract information at the field level, okay, from the field directly. However, I would say that convolutional neural networks or other machine learning techniques, the application of these techniques to actual cosmological surveys, not on simulations, but to actual cosmological surveys, is still an open question, mainly because of the lack of transparency and interpretability of these different techniques. That's not to say that these techniques are bad. On the contrary, I think they have a lot of potential, but there is an obvious issue that is, we cannot deny it, which is the lack of transparency and the lack of interpretability when you run a neural network. So a nice combination of these two approaches has been proposed by mathematicians, in particular by a mathematician, Malat, a French mathematician, a little bit more than 10 years ago, through the wavelet scattering transform. In the context, so this middle ground between these two approaches was proposed, but in another context, okay? In the context of computer vision and signal processing, not related to cosmology. I will explain what I mean by wavelet scattering transform. But first, I want to tell you the power of the wavelet scattering transform. So it was very nicely illustrated in this paper by Cheng and Menard from Johns Hopkins, Sihao Cheng and Brice Menard. that the wavelet scattering transform can be very successful at characterizing non-Gaussian textures for a variety of different physical fields. So you can see, for example, a simulation of the Ising model and the same thing generated with wavelet scattering transforms, sea temperature, solar UV, matter density, that's in the context of cosmology, and it works pretty well. I mean, sometimes better than others, but the wavelet scattering transform, this technique that I will tell you about, works pretty well at reproducing non-Gaussian features. Okay, that being said, let's start to see how does it work, okay? So how does this work? Yes. Say that again. No, the idea will be not to reproduce. The idea from that paper was to show that you can reproduce these non-Gaussian fields, yes, but the idea of what I will show you is not to reproduce these non-Gaussian fields, it's just to extract information from it. Yeah, thank you for the question. So how does this work? So we will have an input field, okay, that we call I naught. It could be, for example, the galaxy density field. In our case, it will be the galaxy density field, or it could be the ALMs of the CMB, okay? In my case, it will be, I used it for the galaxy density field. So, but I wanted to call it in a generic way, okay? So I call it I naught. This is our field that we measure in the sky. Now, the idea is to convolve it with a kernel, okay? You convolve it here with some kernel, and this kernel will be, in our case, a wavelet with a certain length scale and an angular component, okay? So this wavelet, psi JL, will have a length scale given by this superindex L, and an angular component given by this index J. Now, after you convolve it, you take the absolute value, okay, of the modulus of the convolved field to get the local strength of fluctuations. And finally, to construct the translational invariance statistics, you take the spatial average. In a convolutional neural networks, for the ones who are familiar with this goes under the name of global pooling, okay? So you take the absolute value and you take the average. Okay. So in fact, so this is the first layer of the wavelet scattering transform technique. Okay, you take the field, you convolve it with wavelets, which are functions that have a certain length scale and a certain angular component. Okay, and there are different types of wavelets. I will show you. You take the absolute value to take the local strength of the field, and you take the spatial average to make it translational invariance. In fact, the power spectrum, the well-known power spectrum, can be defined in a similar way in Fourier space. Let's look at that. So in this case, in the case of the power spectrum, we convolve the field. Whoops, I didn't want to do that. What? Double click where? Here? Ah, okay. Okay, I will not touch it. Yeah, so in the case of the power spectrum, you convolve the input field, which will be, in our case again, the galaxy density field, with a Fourier mode, okay, a plane wave, e to the minus ikx. And then you take the absolute value and you take the square instead of leaving it without the square. You take the square and you take the ensemble average. See, that is similar to what we do here. Instead of the wavelet, we have a plane wave. We take the absolute value. In the case of the power spectrum, you take the square of it, but it's kind of similar, yeah. However, note that the power spectrum cannot probe the interaction between scales because this plane wave doesn't survive the absolute value squared, okay? So it is a single scale analysis. When you are considering, the power spectrum is given at a certain scale, P of K. You will have different Ks and you can measure the power spectrum as different Ks. But you don't consider the interaction between different scales. So in this sense, I say that the power spectrum is a single scale, gives us a single scale analysis. On the other hand, in our wavelet analysis, our kernel is a local kernel, okay? So for example, I plot here a wavelet at some scale, a wavelet at another scale. These are the types of wavelets that I'm using, okay? So it's a Gaussian, that has some ringing, yeah? A Gaussian envelope with some ringing. And so our kernel is localized. And so we can repeat this process and go on to different layers. And we will have different layers of coefficients. And for each layer, we have a variety of scales. You see, for example, the second layer, you do the following. You take the input field, you convolve it with a wavelet, you take the absolute value, but instead of taking the ensemble average, as we did for the first layer, you convolve it again with a second wavelet, and then you take the absolute value, and then you take the ensemble average. So here you have interaction between different scales, okay? Which is interesting because in non-Gaussian fields, there is an interaction between, there is a correlation between different scales, okay? And we want to capture this. So this leads to a structure. You can go one layer after another layer, okay? You can stop at some point. We did our analysis on a real galaxy survey, and we stopped at the second layer, but you could in principle go on. This leads to a structure of the scattering transform that resembles the structure of a convolutional neural network. But the difference, you see, this is a wavelet scattering transform. You go to, you take a convolution, you have different scales, you take another convolution, and so on. So this kind of resembles the structure of a convolutional neural network, but with the difference that the scattering transform uses a preset library of kernels, okay, which are the wavelets. In a convolutional neural network, you don't know what the kernels are. You're learning them from the data. It's obscured. Here you know exactly, okay? We're not doing any machine learning. You can call different things machine learning these days, but we are not doing any black box machine learning here. We are using a sophisticated statistical method. But so in this case, it's more transparent, the scattering transform, compared to a convolutional neural network. The kernels are not learned from the data. This is why the scattering transform is more interpretable than the usual machine learning algorithms. So what is the information that we are extracting? The first order coefficients encode the information of the strength of the clustering of structures around a given scale, which resembles to some degree the power spectrum, okay? As I showed you, the first order coefficients of this wavelet scattering transform is somehow related to the power spectrum. You can think about it as a power spectrum with more information, okay? The second order coefficients encode information about the clustering of cluster structures. See, here we are taking the absolute value of the convolved kernel with the absolute value of the convolved field. So it's the clustering of clustered structures. And this resembles to some degree the 4-point function, and so on. Okay, so we can efficiently capture non-Gaussian information. By the way, just to clarify, I'm not saying that the first order is the power spectrum and the second order is the 4-point function. That's not what I'm saying. I'm saying that you can think about it in that way, okay? It resembles to some degree what we are used to thinking about in the power spectrum case or the power spectrum of the power spectrum. Yeah? Greco. Sorry? The structure of, this is not a neural network, this is a scattering transform. What I said is that so I'm talking about the wavelet scattering transform. What I said is that it resembles the structure of a convolutional neural network, only because I have a layer that I convolve with some kernel, okay? And then I convolve it again, and I convolve it again. So in that sense, the structure after the different convolutions resemble the structure of a convolutional neural network, okay? So I have different scales, yeah? Different scales given by the scales of the wavelets, yeah? I take convolutions, I take the absolute value. That's how my first order coefficients. My second order is taking a convolution again, taking the absolute value, and so on. Great, yes. Great. So there are different choices that you can make. Actually, today there was a paper in the archive trying to learn the best choice for the wavelets from a convolutional or from a neural network. What we didn't learn it from any neural network. What we did is we tried with a 3D, we were studying a 3D field, so we tried with a 3D wavelet, but there are different choices that you could take. We wanted a localized function, so that's, you know. So today there was a paper claiming that with a neural network you can learn the best possible wavelet for a particular scenario. That's not what we did, and you know, I say this as a comment. I didn't read the paper yet, so I don't know how well they are learning it. Yeah, thank you for the question. Yes. It's a completely different way of thinking about clustering. The only relation that I'm saying is that you take a convolution with something, but in the power spectrum it's not localized, and here is localized. And then you take the absolute value, but in the power spectrum you take the squared. Here you don't necessarily take the square. Well, in fact, what we did in our work is to take the absolute value and then elevate it to some power q and try to find the best power q, meaning the power q that gives us the most information. But yeah. Okay, so what we did with my postdoc, his face is distorted here, but with my postdoc, Georgios Valogiannis, was to apply this wavelet scattering transform to three-dimensional simulated matter fields first. We just wanted to know how the wavelet scattering transform performs in simulations first, okay? And what we saw is that it performs much better than the standard power spectrum statistics for cosmological parameter constraints, okay? So first, what you do in general before jumping into the data, what you do is you first work it out analytically, then you test it in simulations and see how well your technique compares to the traditional method. Well, this technique extracted more, and we compare it in terms of the constraints, the error ellipses on cosmological parameters, okay? So what we saw from simulations, I'm not showing you here the results from simulations, but I'll show you the results from the data. what we saw is that our technique gave us much better constraints on cosmological parameters than the standard power spectrum. Yes, there is non-Gaussian information in the simulations. And this technique is good at extracting non-Gaussian information. So the errors on the parameters become smaller. Now, based on this result, we decided to analyze an actual galaxy data set. So we apply the wavelet scattering transform to the latest release of the BOSS galaxy data set, which is a galaxy data set that has been measured by the Sloan Digital Sky Survey. We incorporated for this many added complexities that come into play when working with actual data. For example, and you probably saw this, the fact that galaxies are a biased tracer of the matter field, okay? We're not dealing with matter anymore, but we are dealing with the biased tracer. You've seen this? A biased tracer of the matter density field. The galaxies are observed in redshift space, and this introduces an observed anisotropy to the clustering. This is known as the redshift space distortion. Okay, we need to include this. In addition, we have a non-trivial survey geometry, the mask, and we accounted for all of this, the mask. We had to deal with the mask of the survey, and we talked about mask. So what we did is we use state-of-the-art simulations that include baryons and dark matter. These are called the Abacus simulations that my colleagues at the Center for Astrophysics have been developing to model the parameter dependence of the scattering coefficient. And once we have the parameter dependence of the scattering coefficients, we run Markov chain Monte Carlo likelihood analysis, and we learned all of that last class. So these are our results coming from a Markov chain Monte Carlo likelihood analysis. And here I'm showing the constraint only for a subset of cosmological parameters, the cold dark matter density, NS, AS, sorry, not AS, sigma 8, and H naught, okay? So here you can see the standard power spectrum in red compared to the constraints coming from the scattering transform in blue. You can see already by eye the significant improvement that we obtain. It's not surprising there is non-Gaussian information in galaxy data, and we have a method to extract more information than the power spectrum. So it's not surprising that our errors are much better than in the case of the power spectrum. Yeah, so basically, I think that this is an efficient way of accessing non-Gaussian information, and our results for this particular case showed improvements ranging from factors of 3 to 8 times over the standard power spectrum statistics, which is the main statistics that has been used in the field over the past 2 to 3 decades. So this is quite exciting. Now, in terms of the tensions, we recovered those tensions that I mentioned before. We still see a tension in the Hubble parameter value and sigma 8 with high significance. And we are currently testing several extensions of this analysis. And we are also preparing to apply this technique to other existing cosmological data sets and upcoming surveys. This technique is, it's not a new technique, but it has, what is new is that it has been recently applied to cosmological data sets. And it's not only valid to be used for the large scale structure. You can use it for the CMB, for other tracers, for, if you are interested in extracting non-Gaussian information from a field, yeah, this technique has certain advantages that I talked about. So I just wanted to present it here. I will skip these because these are details. And I wanted to, well, this is actually what I said for the ones, I don't know if you were here in my talk yesterday, the public talk, but I thought I would say it here too. Before I finish, I would like to give you an idea of the massive, this was a class, this was a course on statistical methods in cosmology. And I think that, the techniques to analyze cosmological data will be becoming more and more sophisticated over the next decade. And we really need it, and we owe it really to the people building the experiments and paying for the experiments, paying meaning the taxpayers or whatever, like I think we will have a lot of data, and we should really exploit it. And why do I say that we will have a lot of data? So there are a plethora of experiments coming up in the next decade that will measure, for example, the CMB with high sensitivity and resolution. We have, well, coming up or existing, okay? And this is just a subset of the experiments. I wanted to mention CUBIC, which is happening in Salta, the province of this country. And there is also a tremendous amount of data that we have and we expect to receive in the next few years from the large-scale structure of the universe. The Vera Rubin Observatory, SphereX, well, DESI is already taking data, JWST, etc., etc. Okay, this is not a complete list of experiments. So, I think we expect to have a wealth of new and complementary cosmological data sets soon, promising major advantage in our yet incomplete understanding of the universe. So I think the future is bright, and we should continue to think about statistical methods in cosmology. Besides this I hope this course served as a fuel for you to start thinking more in depth about different techniques that you may be using to apply to the data in the near future. And with this, I will finish, but I will take questions also. Questions? Yes. Excellent question. Right. You may want to robust, meaning, there is a question of time, right? You may want to, it is robust, but the question is perhaps if you gain more information taking different lengths, right? We consider a certain number of lengths, of wavelet length. If you consider the length too big, you will lose information. You will not be convolving with the smaller scale. If the length is too small, there is a question, you will gain information, but there is a question of how computational expensive it becomes, because you need to make a lot of these convolutions. So, it's a compromise between the two. Right, yeah. Hmm? So your question is if I'm using lambda CDM? Lambda CDM, yes. Is that the question? Yes, we are using lambda CDM. Yes. Yeah, you need to mask it. The same as you do when you consider the power spectrum, right? You mask first and then you apply it outside of the mask. Yeah. Yes. Yes. This was just a comment in general. In simulations or real data, it's not very transparent. You don't know very well what are the kernels that are being used, where the information is coming from. I know that there are lots of methods that are being developed, latency maps and different methods to try to understand where, the information is coming from. But this is you know exactly what you're doing. In that case, it's more transparent, right? You convolve with a wavelet that you know what it is. You don't put it in a black box and take it out from the black box. I know it's not completely a black box, and there have been, you know, um, developments in this area over the past year or the past months even. Um, but I'm not building any convolutional neural network in general. So what people do is you build simulations, okay, that you think could resemble variations of your data, and you train it over those simulations. And so basically, people are trying to extract cosmological parameter errors, and so the question is whether those simulations resemble your data, and what if your data departs from those simulations, would you be capturing it with those? So that's, yeah, it goes under the name of, well, uh, domain adaptation. Like, does it generalize well? Yeah. Um, Probably yes. We didn't use another kernel for, we just stick with, the wavelet that we chose. I will tell you, probably yes, it will depend. It also depends on, at some point we were taking the average over the different angular components. And we saw that if we don't take the average and we consider the different angular components of the wavelet, we gain more information. We will probably also have different, it's not that it's robust or not robust, because it will change, right? But it makes sense that it changes because you may extract more information with different choices of length scale. But yeah, it will, I should read the paper that came up today. But in any case, besides that paper, it will change, I'm sure. I didn't do this experiment, but I'm sure it will change. Yeah. Yes, Xiao. How do you do the marginalized? Same way, right? You have, you consider, so the probability distribution function, you will have it over all, you varied all of the parameters. So in that case, you're already marginalizing the error bars that you get from the MCMC analysis will be marginalized over the rest of the parameters. If you're varying overall, you're making variations over all of the parameters. I don't, what is already marginalized? The likelihood itself? I'm not understanding the question. So from the MCMC, if you vary all of the parameters, you will be able to marginalize over the parameters once you draw the posterior distributions. We should talk about that. I'm not sure I'm following, but we should talk about that, yeah, later. Other questions? Yes. A wavelet is a Gaussian convolved, right? Let me see if I don't have, but wavelets look, it's not, so this is how, well, a plane wave is for the power spectrum, but the wavelets are a Gaussian convolved with some Bessel function, yeah. It's a particular kernel with a particular shape. I mean, I don't emphasize very much the shape of these wavelets because you may choose other wavelets, but it's a local kernel. Yes. How do you compare the observable? What observable? Okay. Ah, great, great. Yes. So how do you know what's the dependence of the scattering transforms with the coefficients with the cosmological parameters? There is no theoretical model for this, right? So what we do is to use simulations to understand. We run different simulations with different cosmological parameters, and we predict the wavelet scattering transform. So we have an idea of how these scattering transforms vary with cosmological parameters. In the first paper, we did it with with a Taylor expansion around the fiducial model, kind of like a Fisher approach to model this cosmological dependence. Now we are doing it with an emulator. The simulations we are using are being developed by another group. They're called the Abacus simulations, as I mentioned. These are state-of-the-art dark matter plus baryon simulations. And we are using, it depends for what test, but we are using other thousands of the simulations. Yes. Each simulation has, but there are many. Yeah, there is a grid. Yes, yes. There is what they call the hypercube grid of simulations. Yeah. Well, okay. With this, I will thank you again, and yeah, I hope to see you all soon.